Hello, awesome mindsetters. This is your best show for learning. Yes, Learn Extra with me, Abram. On a Saturday, hope you're all chilled up and ready to learn more because today it's all about physical sciences. And I'm not alone. I'm with Phil. Phil, how are you doing?
I'm great, thanks. And you, Abram?
I'm awesome. I heard a lot about you also on the page because I posted asking mindsetters who's their favorite teacher, and you came on the list. So I wonder, what are you doing? We're about to find out.
Well, I hope so. Well, today we're going to be taking a look at some exam revision. I'm going to be talking about some acid-base reactions. We're going to be dealing with learning outcome 1 a lot today. That's the experimental stuff, some tables, some graphs. Hopefully you guys can join us.
Nice one. Mindsetters, to join us, it's so simple. One, you need to log on to Facebook. Our Facebook link is facebook.com/learnextra. That's where you can post your questions and your comments. Let us know. Let Phil know, how is he doing? Is he on the right track? Is he covering you well with the questions that might be troubling you? And also, you can also join us on Twitter @learnextra. But lastly, for today's show, for you to kickstart it on a right note, you need to download the notes, which are found on learnextra.co.za/live. I'll be having all the links right on our Facebook page. Let's learn more and learn extra.
Thanks so much, Abram. So, as I said today, we're going to be dealing with some questions. Guys, as Abram says, get on the Facebook page, get that link to all of our fantastic notes. And guys, then you can start copying down with us, get that notepad out, get some calculator, pen, pencil, all your water, get organized with us, and then follow through the questions with us. Once again, just a request to jump onto Mixit, that Curio. It's absolutely amazing. It helps us assess how you're doing, and it allows us to start addressing the questions that you guys actually struggle with. So jump onto that page and start playing around with the Curio questions. And that way you can actually try it as many times as you want. Just a reminder, at the end of your 5 questions, to click submit, and you'll get a mark sheet out and you can try it again and make sure that you get 100% by the end of the process. Okay, well, let's jump straight into it. We're jumping into some of these questions from past papers. Now, just a little bit of a hint. When you go onto the government's website, education.gov.za, and you look for these questions, and in fact, some of those links to these papers are actually on our Learn Extra page, so don't worry about that. But what I'm going to tell you now, and this is a bit of a secret among some of the matric teachers, these papers, the February-March papers, tend to have the slightly more challenging questions. February-March paper to 2009, and we've adapted this from question 8. So if you've got all those past paper questions and you're hoping to go through all of this with us, I'm going to start off with a question about acids and bases. Okay, so the first question we're going to deal with today is talking about antacids. Now, it's a bit of a strange word, but antacids are something that you and I have usually found inside the home. Trade name Rennies, those things that you start to eat after a heavy meal and your stomach's not feeling so great. This is a question about that and how they actually work. So, some learners have decided to conduct an investigation. Now, when we do an investigation, we're dealing with learning outcome 1. Now, learning outcome 1 tells us how to deduct things from investigations, how to draw up tables and graphs, draw conclusions, and even come up with our own investigations. So stick with us today, and we're going to be talking about these antacids. So here we go. We've got these antacids, which are used to relieve indigestion. So that really uncomfortable feeling that you get after you've eaten a very heavy meal or certain types of foods. Indigestion is the condition when the stomach produces too much acid. Okay, so there's too much of that stomach acid, that HCl for those life sciences learners out there, resulting in an uncomfortable and painful feeling. A certain antacid tablet, so this is something which acts against the acid, dissolves in water and reacts with the acid in the stomach to release carbon dioxide gas. So this is a product of my reaction. Now it says, name the type of chemical reaction that explains why antacids bring relief from indigestion. Now this is a bit of a tricky one. Now this is something that you might have learned as a part of your equilibrium, but I want you to read through the description and see if there's something that doesn't stick out to you. Some of the words that I've highlighted might lead you to the correct conclusion. You might even remember this from grade 10, of the type of reaction. Now let me just remind you of some types of reactions. Redox is a type of reaction. Acid-base, double displacement or single displacement, these are all types of reactions. Even a precipitation is a type of reaction, decomposition or synthesis. Now, does any one of those ring a bell when we start to talk about an antacid? There we go, there's the answer. It's something to do with the acid inside my stomach. So the type of chemical reaction can be described 2 ways. Either it's an acid-base reaction, and this is the most common way of describing it. An acid-base reaction is one where an acid reacts with a base. Now, another way of describing it, and this is also correct in the memo, is called a neutralization reaction. So what happens is the acid goes inside your stomach, and so does the antacid, and they neutralize each other. So it's neutralization, and these are both correct. Remember, there's just one mark, so it's either an acid base or a neutralization type reaction. Okay, I'm getting a bit tongue twisted there. So acid base or neutralization. So this is what's happening when I have the acid inside my stomach from the food. My body naturally produces the acid, sometimes too much. I eat the rennies or whatever might be the antacid, and then it neutralizes that acid inside my stomach. But now that's not all. This is going to lead us on into a learning outcome 1 type question. And here it comes. It says a group of learners wants to investigate the effect of temperature. Okay, so now what's happening over here is an effect of temperature on, and this is very important, the rate of dissolution. Okay, so let's just stop there for a second. They want to see if temperature has an effect on how quickly these tablets dissolve. So I'd like you to grab a highlight if you're going through this with me or writing down notes. Make sure that you take notes of some of the important things. So the effect of temperature on rate of this antacid tablet in water. Design and investigation. Okay, now this is where things get really challenging because you've got to come up with your own investigation that the group of learners can conduct by answering the questions that follow. Okay, now grade 12s, this is a section which is going to come up time and time again. Anytime there's learning outcome 1 in your papers, and that's every time, you're going to find out that there is an investigative question, there's a hypothesis, a dependent and independent variable. There's lots that you can do. So now the first question, I'm going to show you how to do this properly. State an investigative, now this all seems a little bit complicated, an investigative question, okay? Now this is not something that a detective is going to use to question a suspect. This is something that you're going to ask of the learners who are conducting the investigation. So here we go. We've got to have a question which asks a question about this experiment. The question is, how do we actually come up with a good investigative question? Well, here's your guidelines. An investigative question must contain the variables that you're going to be talking about. So let's try and see if there's something that we can find in the description which leads us onto the variables. So there we go. So the effect of temperature is a variable. And there we go. Rate of dissolution. Okay, well that's quite interesting. So what can we actually measure? We can measure the temperature and the rate of dissolution. Now, anytime you see the word rate, that's a link up with time. So now what we can say in our investigative question, and please make it a question, so you must end off with a question mark at the end of your investigative question to get your full 2 marks. So let's start to put together a good investigative question. So, does temperature affect the rate of dissolution? So make sure that you end that off with a question mark. So does temperature, so there's my first variable, affect the rate of dissolution? So here we go. They've actually given you the aim, and you can change that into a question. So the effect of temperature on the rate of dissolution. Now that's an aim. But the investigative question is saying, does temperature affect the rate of dissolution? Or does temperature affect the time that it takes to dissolve a tablet? Those would be good examples of an investigative question. Okay, but now here is a question which is asked so often in your exams, and people are not sure how to answer this question properly. The next one is a hypothesis. Let's make sure that we understand what this word hypothesis actually means. A hypothesis is a testable prediction. Now what they're looking for your 2 marks, just to remember that this is 2 marks for a reason. They want to see both your variables, and they want it to be in the form of a prediction, something which will happen in the future. Please don't describe it as something which already happened. So now let's make a prediction about the rate and temperature's effect on it. So what we can do for our hypothesis is to make our prediction. So let's make a prediction together. At higher temperatures, the rate will be faster. So let's go through that again. At higher temperatures, the rate will be much faster. So I've included both temperature and rate. Or you can say at higher temperatures, the tablets will dissolve quicker. So there's a reference to time. You need to have both your variables, so that's time and temperature, and also you need to make sure that it's in the form of a prediction, something which will still happen in the future. You're describing what might come out of my experiment, and that is a good hypothesis. There are two parts to this. So first is your variables. The second part is it must be a prediction which you can test. Now over here, this is where things are going to get particularly tricky. It says write down a procedure. Now again, let's concentrate on some of the words here. A procedure is like a recipe, something which somebody can follow, that can be followed in this investigation to test your hypothesis. Okay, so to test the hypothesis that at higher temperatures the tablet will dissolve faster using some or all of the apparatus and chemicals listed below. Okay, well, let's see what they've given us, and I want you to start thinking through all of these things and why they might be necessary. So let's just go through these pieces of through these instruments, and let's actually see if they're necessary. Well, just think about the variables and how we're actually going to get this done. This is just like baking a cake. I'm absolutely going to need an oven. I'm going to need an oven, a cake tin, and we're going to make sure that we've got all of our ingredients, all of our apparatus, and let's see which one of these are necessary. We're not going to use the whole kitchen, remember, but let's see what's necessary. A thermometer. A thermometer measures temperature, so I definitely need that because temperature is one of my deciding factors over here. In fact, a thermometer is going to be measuring my independent variable. It's going to be measuring temperature. Now, stopwatch. Why would I need a stopwatch? We're not running a race here, but remember that we're trying to measure the rate or the speed of a reaction. So definitely I need a stopwatch to tell time, which is my dependent variable. Okay, so now we've got some other pieces of information over here. We're told about a hot plate, a beaker, a measuring cylinder, a spatula or teaspoon, and then we've got water and our antacid tablet. Well, absolutely, we need the antacid tablet, that's for sure, because our antacid tablet has got to dissolve. And we're going to need the water to make sure that it's got some way to dissolve. Why would we need a beaker, a measuring cylinder, and a spatula or a teaspoon? Okay, we'll start to think about this. Let's see how we could actually put this all together to change what we're doing. Now, let's for instance say the beaker. I need a place to do my reaction. I need to actually have a container. So if I've got my beaker over there, what I'll find is that I've actually got a place to do my reaction in. So if I'm doing my reaction in the middle there, I've got a place for my tablet to start dissolving and giving off its bubbles. So I absolutely need to have this in. Now, they start to talk about a hot plate. This is the only way that I've got to control the temperature. So if I've got a hot plate underneath there, that allows me to control my temperature. Now, just a reminder that I need to be able to put in my thermometer to measure the temperature at all time. So my thermometer's got to go inside there, and just a reminder that we've got to put it inside my liquid with its little nodule down at the bottom there, with the readings up top here. My thermometer absolutely has got to be inside my liquid, and it's got to be measuring it at all times. Why would I need a spatula or a teaspoon? Well, a spatula or a teaspoon is used to get solids out of containers, something like an antacid tablet. This might be the way that I use to get my antacid tablet into my solution. And something else which is quite important as well is my hot plate needs to get my solution up to a certain temperature. Now be very, very specific about this. They're looking to see if your method will be precise. Now, to be precise means that you can repeat your experiment many times and still get the same results. So all of these things will actually help you, and very importantly, my teaspoon is going to allow me to stir my solution to get the same temperature throughout the entire liquid of water inside that beaker. So that's quite important as well. But what about this last piece, the measuring cylinder? Why on earth would I need a measuring cylinder? The measuring cylinder is there to make sure that we have the same amount of water each time. So when I'm pouring in this water, so my measuring cylinder has got to pour in the same amount of water each time. And that allows me to be absolutely accurate and precise. So my measuring cylinder allows me to add in the same amount of water every single time. So what I've got there is my hot plate to increase the temperature, my measuring cylinder to measure out the same amount of water each time. I want you to think about that. Why would I need the same amount of water each time? And what do I call that type of variable? Now, the measuring cylinder allows me to control the amount of water. Water will affect my experiment. The measuring cylinder is there to allow water to be a controlled variable. It's absolutely important that you know what a controlled variable is. Even though we didn't ask it, a controlled variable is a variable which might affect my experimental results, but I'm keeping the same for all of my experiments. Very important that you know that. So what we're going to do is we're going to finish off this question now. Now what we've got to do is we've now got to prepare my experiment for having some results over here. Now it says to draw a table that can be used to record the results. Now let's just remind ourselves what these results might be. Indicate the relevant headings, and this is what your examiners are looking for, of the rows and columns inside the table. No values are required. Okay, so I'm just going to point out some of the properties that your examiners are looking for in a good table. Now your headings very often have to have units inside them, and they've got to be as descriptive and precise as possible. So let's come up with a good heading. So what we're going to do is we're first going to list the variable which we are going to change. That is your independent variable. Your temperature is very important because the temperature is the thing which I'm going to change. Very often underneath a good heading you would put the unit in degrees Celsius. So there's my first heading. Okay, but then what we're going to do is we're then going to record time. But what I'm actually going to do is I'm going to record 2 times. So what I'm going to do is I'm going to record time twice. So what I'm going to do is I'm going to say that there is time which is recorded in seconds. But why am I doing it twice? What I'm doing is I'm repeating my experiment twice for each temperature. I want you to think about why I might be doing that. So temperature, well, temperature I'd like to do twice, and I'm actually going to leave a final column there as well. We're going to do this a few times. We need to record at least at a few temperatures. So there's temperature 1, temperature 2, and temperature 3. You don't need to put in values, but I suggest some values of temperature which is at room temperature or above. Remember that we've only got a hot plate. So something like 30, 40, and 50. Make sure that they're regularly spaced if you are going to put them in. You don't have to put them in. Now what we're going to do is we're going to record 2 times at 30, 2 times at 40, and 2 times at 50. And then of course what we've got to do is we've got to find the average. You might ask yourself, why are we recording each experiment or repeating each experiment twice? And that is to increase the accuracy of my experiment, and it's also to test my precision. If these 2 times are very different, my experiment has not been precise. We might still be accurate on the average, but what we're doing is we're testing the repeatability. And it's always a good idea to repeat your experiments multiple times. If the experimental results are close to each other, we call them precise. If they're close to the true value, we call them accurate. Okay, so there we go.
All right, Phil, I have a lot of questions that are on the Facebook page.
Are we going to give them some breathing time?
Yes, let's give them a breathing time, then
Okay.
we'll take all those questions after the break.
Great, no
Is it
problem.
cool? Right, Mindsetters, also after the break, I'll be telling you more about the After Earth winner on our competition. See you after this. Welcome back, Mindsetters, and as promised you, I'll be telling you now the winner for our After Earth competition from the Thursday's show. The winner is Kayla Harris. Congratulations to you. You can go watch the movie. Your tickets will be on your way very soon. Watch out your emails and check out our communique with you. But otherwise, Mindsetters, thank you for entering the competition. Also, Kayla Harris, you've won yourself double tickets and also this awesome hamper t-shirt and a book and then this awesome pen. But otherwise, what I also need to tell you is that The QR code for your lesson is PS12 on Mixit. The instructions are right on the Facebook page. Now, Phil, before we continue, can I give you the questions that the Mindsetters have?
Absolutely, guys. I'm glad to see you sharing on the page.
All right, the first one is from Liz Leonard Mtungwa. It says, is it wrong if I write, does temperature affect rate or reaction?
Okay, now it does address both of them, but we've got to be a little bit more specific about the investigative question. Now, it should refer to something in our actual experiment. So it should say rate of dissolution of our antacid. So we've actually got to refer to the thing that we're talking about. Now, your examiners probably would give you the marks there, but we've got to get a little bit more specific to make absolutely sure. There was another nice question after that,
One
wasn't
last
there?
one, it's from Penyo Koza. She says, I'm confused. My physical teacher said that your investigation question must not be one that needs a yes or no answer.
Okay, it's some pretty good advice. Your investigative question should actually ask what the effect is of temperature on your rate of dissolution. It's better not to have a yes or no answer to that question. So instead of saying, does temperature affect the rate of dissolution, we could say, how does temperature affect the rate of dissolution? Then we're looking for a relationship between temperature and the rate of dissolution. So your physical sciences teacher is actually correct there. They should actually make it a question which allows us to find a relationship between those two variables. That's actually the best way to do it. Okay, so some really nice questions.
Well said. Let's continue.
Fantastic.
Yes.
Okay, so the very, very last thing that they're asking us to do, and they're asking us to apply some of our knowledge. Okay, so we're back into our knowledge and we're back into rate of reaction. It says, is it better to take the antacid tablet with warm water or cold water? And give a reason for your answer. Okay, now we've got to say, well, from my learning outcome 2, from my knowledge of actual rates of reactions, should I be dissolving this tablet in warm water or cold water? Now, just a reminder that temperature does affect the rate of reaction. So what we can say is that temperature has a direct effect, or at least a directly proportional relationship. Now, let's just rephrase that in some slightly easier English. The warmer the water, the faster the reaction. And I want the reaction to take place in my tummy. I want that pain to go away as quickly as possible. So what I'm going to do is I'm going to choose warm water. So I'm going to choose warm water because, and this is where they're looking for my understanding, is that at a higher temperature means a faster reaction. So at a high temperature, we will find a fast reaction. And that's exactly what I want, because I want to get relief from that excess acid very quickly. So a high temperature means a faster reaction, or results in a faster reaction. And that's really, really important, and that's what they're looking for. They're looking for your understanding that a faster reaction is a result of a higher temperature. Sorry, let's just neaten that up for anyone taking notes at home. There we go. Let's just make sure that that's nice and neat. Okay, so a faster reaction is a result of a higher temperature. So I'd rather take these with some warm water. Okay, so some really nice learning outcome 1 stuff. We're dealing with experimental stuff. We're trying to find out the meanings of hypotheses, investigative questions, and guys, you should expect something like this in your finals. They love to see if you can understand experiments in a context of an exam. Now, rates of reactions is very likely to be the place that they ask this type of question. So I'm very glad that this was covered today, that we investigated investigative questions and hypotheses, and we even dropped some tables, which is kind of unusual, but it's very useful to know the structure of a table. Independent variable on the left, dependent variable on the right. So we had temperature on the left and time on the right-hand side. So I'm hoping that you understood the structure of my table over here. And what they very often ask you to do is to actually take results like this and turn it into a graph for a good number of marks. But let's move right onwards. Let's actually deal with another experimental question. It says, in a certain mass of calcium carbonate, now this is no mistake, calcium carbonate is actually the contents of most of those antacids. Calcium carbonate is better known as chalk. Okay, so the next time your parents start eating away at those rennies, you can laugh at them and you can say that they're eating with chalk. Okay, and calcium carbonate is actually the chemical name for antacids and for chalk as well. But it's very, very good at getting rid of your stomach acid, and it also gives you calcium, which you need for your bones and teeth. So here we go. Calcium carbonate chunks is added to hydrochloric acid. So there we go. We've got a base, and here's our acid in an open beaker. It's quite important that we note that this is an open beaker. because it allows things to escape out the top on a scale as shown below. So let's take a look at our picture on the screen over there. We've got this open beaker over here. We've got our calcium carbonate, our CaCO3, my hydrochloric acid, and I hope you remember that hydrochloric acid has the formula HCl. And it says the equation for the reaction is as follows. So let's just go through our reaction with a highlighter. So there we go. We've got our calcium carbonate, which is a solid. Very important that we know that. Hydrochloric acid, which is aqueous. Okay, so it's a liquid form. Now, here's our products. Very important that we note the phase of my products. We've got calcium chloride, which is aqueous. We've got water, which we know is a liquid at room temperature. And then here's the really important one. Carbon dioxide is a gas. I breathe it out all the time. Carbon dioxide is a gas. Now, this is the reason that the mass is going to change, because gases can escape from the top of a beaker. Now it says CO2 gas is allowed to escape from the beaker. The data in the table below was obtained for a time interval of 8 minutes. So here we go. We've got a table over here. I'm hoping that you can see what's going on here, but I'm just going to highlight some very important pieces. So we've got our independent variable over here, which is time. Okay, it's listed on the left-hand side over there. Then the mass of the beaker and its contents. Now I want you to see what happens to the mass of the beaker. At time 0, we've got the full mass of the beaker and its contents at 200. By the time it reaches 8 minutes, we've got a drop in mass. So then we've got 184.8, and that is our final mass. So what's actually happened is the mass of our beaker has decreased. Okay, now let's get into the questions about our reaction over here. We've got our beaker, we've got our calcium carbonate with the hydrochloric acid. Let's discuss some of the questions. It says that rate in science refers to something that happens in a certain amount of time. Explain. Now we've got to be very careful when we do explain. Explain the term reaction rate. Now they've given us a little bit of a hint. We've got to include time in our description of a reaction rate. Now a reaction can be described in 2 separate ways. Now let's first start with the word rate. Rate is described as the amount of something per unit time, or how quickly something is happening. So a reaction rate. What is a reaction? Well, a reaction does 2 things. A reaction can make a product. So that's our first description. It's the amount of product that we form per second or per unit time. So it's how quickly I manufacture products, or it's how quickly I use up reactants. That's the other thing which a reaction rate can do. So let's just go through those again. A reaction, and specifically a reaction rate, is the amount of product which I produce in a certain amount of time, or it's the rate at which reactants are used. So I hope that's quite clear. There's a couple of ways that we can do this, and very often rate is given as the change in amount over the change in time. So what we can do is we can talk about the change in amount of products, or the decrease in the amount of reactants. So it's the amount of change of product or reactants over a certain amount of time. Now, it's asking us to calculate the change in mass of the beaker and its contents during the 8 minutes. Wait a minute. There's some numbers in the table which can help me out. Well, I can see on the scale that initially my reaction started out at 200 grams. There it is on the table. So 200 grams is my initial. My final mass is 184.80. So what's happened over there is I've changed from a final value of 200 down to an initial. And a lot of you are saying, okay, well, where's the formula for this calculation? Guys, please, 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 don't just rely on formulae. Think for a moment. When I start to see change, I'm looking for delta something. So it says change in mass. So all we actually need is 2 masses. So this one's quite easy. All that I've got to do is to find my change in mass, is to say, and anytime I see that triangle, that delta sign, I say M final minus M initial. So what I'm going to find is that that is going to say M final, which is 184.8 minus 200. Okay, so what's happening over here is I'm going to find out how much the change in mass is. And over here, what I'm going to find is that there are negative 15.2 grams. I have lost 15.2 grams during this reaction. Okay, that's pretty important. I found out that I went from 15.2 grams down to arrive at my final mass of 184.80. Let's just double check that we've got the right values. There we go. We've got our initial value. So there we go. There's my mass initial. There's my final. So I've taken my final and subtracted my initial. So what I've landed up with is a loss of 15.2 grams. Okay, now here's where some of your grade 10 and 11 chemistry comes in. Now it says use your answer in B to show that the average reaction rate during the 8 minutes is 1.9 grams per minute. So we're using time in minutes and we're using grams for our answers over there. Now remember that formula I gave you initially? Rate was the change in amount over the change in time. So I know that my rate is equal to a change in mass over a change in time. So I'm going to use 15.2, which was the change in the amount of my product, that many grams, divided by my change in time, which is 8. And if we put that into our calculator, let's actually do it together, we'll actually get our final answer there. So we say 15.2, which is my change in mass. Let's use the fraction button on our fantastic Casio calculator there, and then we divide it by 8 minutes, and what we find is 1.9 grams per minute. So that's the average rate of formation. So there we go, 1.9 grams per minute. Okay, so that's pretty cool. We've actually studied the meaning of rate, we've done a calculation, and we worked our way through all of this. Now it says, calculate the mass of calcium carbonate consumed during the 8 minutes. Now this one is a little bit more tricky, and you can see that it's a longer calculation. There we go, 5 marks. So what I'm actually going to do is I'm going to make some space down at the bottom, and we're going to go through this. Because remember that this is a stoichiometry chemistry question. Now, a lot of you are saying, oh, what is that word, stoichiometry? This is to do with moles, guys. The only way that I can get from the amount of one chemical to the amount of another is to use moles. It's the universal chemistry language.
Would you like us to take another break just after that one?
So what I'm going to do is, just before we do, I'm actually going to ask the learners to calculate ahead of us. During that ad break, I want you guys to get working at this. So I want the mass of calcium carbonate. Guys, get going with that.
So you have a challenge, guys. Make sure that you get that on Facebook page and let us know. We'll take your answers after the break. See you. Welcome back, Mindsetters. Now, you might have seen from the ad, we are having a career indaba on the 20th up until the 22nd of June at Senton Convention Center. All you need to do is to register online. It's all for free. Go there and help yourself and also understand which careers are suitable for you. If you haven't made that choice, this is going to be a great opportunity for you to be exposed in different careers and help you choose the best career choice that you could ever have. But also, I just want to send this shout out to all the Mindsetters that are on the page, specifically Reflex Matire and Patience Peti Khal Mabusha, which is her birthday today. Happy birthday to you, Patience, and keep learning with us on your birthday. Thank you, Phil.
Thank you so much. Hopefully we can give you a matric higher mark, a higher symbol for your birthday.
As a
How
birthday
about that?
present. Yeah.
Absolutely, a better matric.
Yeah.
Okay, well, awesome, guys. I'm glad that you guys are working through this. I can see you starting to ask some questions on the page. Really nice of you. Okay, now, before we went away on the break, we said how much calcium carbonate, so how much chalk is consumed during this chemical reaction. Now, the only information that I've got is that I manufactured a mass of calcium carbonate of 15.2 grams. So the mass of CO2 was equal to 15.2 grams. That's how much product I made. Okay, now we want to know what is the mass of calcium carbonate. Okay, now this is a little bit tricky because I want to know what is the mass of calcium carbonate, how many grams of this do I consume. Okay, well, here's the problem. You cannot use ratios on mass. You cannot, please, absolutely, you cannot use ratios of mass, because this is like comparing lead to feathers. You cannot do it. The same number of both has a different mass. The only language which these two both speak is moles, guys. If you're given a mass and you're asked to calculate quantities, your first step always should be calculating moles. Okay, so let's take our 15.2 grams of carbon dioxide and let's see how many moles of carbon dioxide we've got. So there's our step one. Our step one is always to convert into moles. So step one over here, let's find out the number of moles of carbon dioxide. And the way that we do this, I hope you remember this from grade 11, and I hope the grade 11s are watching this as well, is that I take my mass and I divide it by the relative molar mass of carbon dioxide. So let's use the mass of carbon dioxide. There we go, 15.2 grams. That's how much we made. That is the mass of our sample of carbon dioxide. Now, where do we get my relative mass? The relative mass is all of the atoms inside the formula, all added up. So if I take my mass of carbon, if you look on your table, should be 12. My mass of oxygen is 16, but remember that there are 2 of them. So 2 times 16 over there. Okay, and then we can put that all into my calculator, and then we can find out what my molar mass is. So it'll be 15.2, and on the bottom there we find 44 grams per mole, and that way we can find out the number of moles that we've got. So let's just do this together. So I say 15.2 over there, let's put it in our fraction again, and 44 grams per mole for carbon dioxide. That's how much 1 mole of carbon dioxide weighs. There we go. So we've got our number of moles of there. So just round to 2 decimal places over here. We were only given 2 on our table there. So 0.35 moles of carbon dioxide. So 0.35 moles of carbon dioxide. Okay, so that's how many moles of carbon dioxide I've got. The question is, how do you get from moles of one substance to moles of another substance? And the way that we do that is using our balanced chemical equation. We use the mole ratio. So let's do exactly that. So that's our next step. Let's use the mole ratio from carbon dioxide to calcium carbonate. So there we go. Step 2 is to use our mole ratio. Let's just talk about that. There we go. So then we talk about our mole ratio. Okay, so our mole ratio of carbon dioxide to calcium carbonate. Now, lucky for us, in our balanced chemical equation, if you take a look at your balanced chemical equation, and let's just do this in another color so you can see exactly what I'm doing. 1 calcium carbonate combines with all the other chemicals to give me 1 carbon dioxide. So they have a 1-to-1 ratio. Now that sounds very technical. Let's just describe it again. 1 of these will make 1 of those. Because my chemical equation tells me that 1 of these makes 1 of my products, that gives me a 1-to-1 ratio. So there we go. For every 1 carbon dioxide, I will need 1 mole of calcium carbonate. So that means that my carbon dioxide, which has 0.35 moles, how many moles of my calcium carbonate would I need? Exactly the same amount, 0.35 moles as well. I know that I've got a number of moles of calcium carbonate, and that is equal to also 0.35 moles. Well, that's fantastic. Now we've just got one last step. We've got to convert back out of moles. Now, to do that, we're going to use exactly the same equation we did before. So in step 3, now I'm going to be dealing with calcium carbonate. So my number of moles is equal to the mass over the molar mass. So let's write it down. And you might notice that I've started labeling all of my mole numbers over there. So the number of moles of calcium carbonate, this is for your examiners and for you, so that you don't get confused, and this is a great habit. Number of moles of what? Oh, I see calcium carbonate over there. So I know exactly which calculation I'm doing. So my mass of my relative mass. Now, I'd advise that you always write down the formula first, substitute, and then manipulate. Because of the ways that the papers are marked, even if you substitute a wrong value inside here, you'll still get one of those marks for your method. Okay, so let's put in my number of moles of calcium carbonate over here. And that was equal to 0.35. Okay, I don't have my mass, that's what I'm looking for, but my relative molar mass, Not too difficult. Look on your table. Mass of calcium, 40 grams per mole, plus 12 for carbon, plus 3 oxygens, and each oxygen is 16. So if we take a look at that, what I'll find is that I've got 0.35 is equal to M, and I like calcium carbonate because it works out very nicely to be 100 grams per mole, down at the bottom there. Now, the only thing left to do at this stage is to multiply it all out and get my mass of calcium carbonate. So my mass of calcium carbonate is equal to 0.35 times 100 grams per mole. So my mass of calcium carbonate over there is equal to 0.35 multiplied by 100 grams per mole. And there we go. If you multiply all of that out, I should get 35 grams of calcium carbonate. And if you were working ahead of me, I hope that you got similar answers. If there's a slight difference in the rounding, don't worry, your examiners are going to allow for different amounts or at least different significant numbers. So if you got something around about 35 or it rounds to 35, fantastic. That means that you know what you're doing in terms of stoichiometry, in terms of mole calculations. One last question that we didn't answer before we went away on the break. It's quite an important one. It says, use collision theory. Okay, now this is really important. Guys, they really like to ask questions about collision theory, and they're always worth about 3, 4, or 5 marks. To explain how the rate of the above reaction will change when powdered. Okay, now that's quite interesting. Powdered calcium carbonate. Now we've got to say, what is the difference between normal calcium carbonate and powdered calcium carbonate? Is used instead of calcium carbonate chunks. There we go, there's the difference. So, how does a reaction know that there's powder or chunks, and how does it react to that difference? Okay, so let's try and figure out what's the difference if I've got these large chunks or if I break it up into this fine powder. Now just picture this. If you were trying to spread baby powder out onto your arms and you started off with a nice big lump, it wouldn't be very easy. The easiest way to spread baby powder onto your arm is to make sure that it's a powder, because powder can reach more places and it's easier to spread. So there's my first clue. The biggest difference between powder and chunks is the surface area. Okay, so powder and chunks have got different surface areas. Now let's just break this down. Let's make sure that we've got a little bit of space. I'm going to show you where your marks are coming from. Okay, so the first thing is that powder has an increased surface area. So what we can say is that powder has more surface area. And that's very important because surface area changes how reactions happen. So it has more surface area. Okay, now the reason for that is because those insides of those chunks have been broken up and exposed. Now I want you to think about the difference between two materials which have got large grains and small grains. Powdered materials always have the insides of those chunks exposed. If you break up a rock to make it into sand, you're actually looking at the inside of that rock. You're reaching more places on the inside of that chunk. So powder has more surface area. Now they said use collision theory. We've just identified the difference. So there's my first mark. I've identified what's changed. Now let's see how we use it to explain the effect on the rate of reaction. So what does that mean? That means that there are more collisions occurring on the surface because that HCl can actually reach inside the chunks. And here we go. So there are more collisions. More collisions with the surface of the solid. So there's more collisions with HCl and our calcium carbonate. So calcium carbonate and HCl can touch each other better if there's more surface area happening over there. So there are more collisions between HCl and calcium carbonate. That is one of the requirements for what is known as an effective collision. Effective collisions are ones which occur when you've got a successful reaction. So here we go. So more collisions with HCl and calcium carbonate. Therefore, more effective collisions. They're looking for these. So effective collisions are the ones which result in products. They're looking for these keywords. And then one last thing to tie this all up to get your third marks. Therefore, there's a faster reaction rate. So this is a prediction from all of this. So a faster reaction rate means that there are more effective collisions happening every second. So let's just go through this again. The first thing which we're dealing with is the thing which we have changed. And there it is. Okay? The change between powder and chunks was a change in the surface area. So we've identified that. Now the next thing which we did was we explained microscopically what's going on inside those chunks. That means that there's more space for collisions to take place. Remember that to get two things to react, they must actually touch each other, and they must collide with each other. And this is what's happened over here. More collisions, so that means more effective collisions. And effective collisions are the ones which actually allow a reaction to happen. Now, if you want to be very specific, you could actually say more effective collisions per unit time. Now, that sounds very technical. All that's basically saying is that for every second that goes by, there's more collisions happening inside each second. And then we've got to make our conclusion, or at least our prediction. That means that I've got a faster reaction rate. So that means a reaction is going to happen in a shorter space of time. So let's just go through these again. So first of all, a higher surface area means more collisions and then a faster reaction rate. I particularly like this question. Now, the obvious follow-on to reaction rates is dealing with equilibrium, and that's where we're going to be moving our focus. And I actually want you guys to get onto Google to start taking a look on the page. So I'm going to introduce the next one before we take a break. And this one I particularly like. I want you guys to go find this because it's quite a wordy question. Our third question over here is from the March 2009 paper. It's question 9, and here it is. It deals with smog, or atmospheric pollution. And it deals with a very important reaction that happens inside engines. I'm just going to highlight it because there's a lot of writing on your screen at the moment. So here we go. There's a reaction which happens inside engines. I want you to notice that it's a reversible reaction. Guys, I want you to write this down. And then, very importantly, it tells you that the delta H for this reaction is positive 90,4 kilojoules. So what's happening over here is I've got a reversible reaction. The forward reaction is endothermic. Really, really important that you know that. So what I want you to do is to start playing around with temperature and this reaction before we go for an ad break. Abram, how's the page looking?
So many questions, but then I think we can tackle them after the ad break.
Absolutely.
Right, Mindsetters, do not go anywhere, but be on Facebook page. Our Facebook page is facebook.com/learnextra. After the break, I'll be telling you more about what's happening on June 16. Don't move. Welcome back, Mindsetters. Now, to help you understand and help us assess you, we are having a Curio on Mixit. So make sure that on your cell phone now, you go to Mixit and make sure that you fill in the assessment. Your code for this show is PS12. We'd really, really like to know how are you finding the lesson, so Phil can see where are you struggling and what can we work on next time. But also, I need to tell you about June 16. Two things are happening. One is that it is Father's Day, so we are having a special message box just for you. You can just drop your messages on our facebook.com/learnextra. We have an event there where you can send us your messages, and who knows, your message could be displayed on our channel during that day, and tell your dad to watch and see the message that you have for him. Also, it is June 16. We're celebrating young people as it is Young Youth Day. So don't forget also that one. More details are on your Facebook page. Phil, let's take it away.
Thanks so much. Well, before we went away on our ad break, I started to discuss an equilibrium question with you. The way that I knew it was an equilibrium question was we had a reversible reaction. So guys, here it is. It starts to deal with smog. Now, smog is atmospheric pollution. It's that very sort of thick brown and sort of hazy color, and you might notice it over some of the cities, especially in winter. So it says smog refers to a very unpleasant condition of pollution in certain urban environments. It's largely produced by the action of sunlight on exhaust gases coming from cars. Okay, so now it says two groups of compounds emitted from car exhaust that contribute to the formation of smog. Okay, now here's the really important ones. So nitrogen oxides, these are some of the smog, and especially nitrogen oxides tend to form a really nice brown color in the air. It says, and unburned hydrocarbons. Okay, now unburned hydrocarbons can be sort of grayish, they can be black, all sorts of things, especially if you're traveling behind a big truck, you can see that black smog coming out of there. Okay, now we're going to deal with nitric oxides. Okay, so here we go. Nitric oxide, or NO, forms in internal combustion engines. Now you might say, okay, well, where are those? We've got to stop those. Okay, well, guys, internal combustion engines are the things which drive cars and trucks. So you can't really take all of them off the road. So internal combustion engines are engines which power cars and trucks by the direct combination of nitrogen and oxygen. Okay, well, you might say, well, then we should just stop combining nitrogen and oxygen. Well, guys, if you're paying attention, nitrogen and oxygen is the mixture of compounds that we actually find in air. Air is 78% nitrogen, the rest is oxygen and a few other small gases, according to the following reversible reaction. Okay, so nitrogen and oxygen, which are already there, combine in this reaction to give NO. Now, you might say, okay, well, why is that so bad? It just looks like nitrogen and oxygen, that's what's in air. But NO can actually go on to form nitric acid inside your lungs, and very often it can make people's eyes yellow, and really, really bad stuff for you. In fact, it causes something called oxidative stress inside the body, and it really makes you tired and down. Okay, now it says, in air, nitric oxide is rapidly oxidized into nitrogen dioxide. Now guys, if you've been studying your Ostwald process, you'll know that nitrogen dioxide is only one step away from forming nitric acid. Now here's the other problem, that initiates reactions responsible for the formations of smog. Nitrogen dioxide acts as a catalyst for the formation of ozone as well. Okay, now you might say, okay, well, ozone, there's a hole in the ozone layer. What's the problem with making some more ozone? And just for those of you that are at home and want to read up about ozone, ozone has got the formula of O3. Okay, it's a special type of oxygen. Okay, now ozone, when it's on the ground, is really, really bad, and it's very, very toxic for you. In fact, ozone is so reactive that it actually eats rubber. So what actually happens is organic compounds, like especially in your skin and rubber, organic compounds are oxidized by ozone, and that's a very bad thing. It bleaches things. Guys, ozone is bad news when it's down on the ground. I want ozone up there in the stratosphere. I want it, 50 to 100 k's off the ground. I want it protecting me from UV light. But the problem is ozone down at the ground is really, really bad news. Okay, now then they go on to say, and there's a long essay talking about, although it's an essential UV screen in the upper atmosphere, ozone is an undesirable pollutant in the lower atmosphere, so this is where we are. It's extremely reactive and toxic, and breathing it in, is really, really bad for you. Now, it talks to you about certain groups of people that are badly affected. So people who are asthma sufferers, okay, people who have breathing difficulty there, sports people, and the elderly. Okay, now it's really important to note who ozone affects. Now it says before the Olympic Games in Beijing, authorities, okay, now just think about Beijing. Beijing's in China, there's a lot of people, a lot of cars, and specifically a lot of pollution over there. So it says, the authorities were extremely concerned about the levels of smog inside the city. Now it says, explain why high smog levels are especially dangerous for sports people. You might think sports people are nice and fit and strong and healthy people, but just remember that sports people are doing a lot of exercise. So to do exercise, think about what you start doing when you exercise. You start to breathe very deeply. This means that the smog and the ozone and the nitric oxide can find its way into your lungs much more rapidly. So they're expecting you to realize, oh, okay, a sports person is going to be breathing a lot more, and the more a person breathes, the more smog can actually enter their lungs. So that's a little bit of common sense over there. You've just got to read very carefully. Now we're going to get into some chemistry over here. Okay, now it says, suggest 2 ways of reducing NO in urban areas. Now, guys, this depends on how much extra reading that you've actually done and how much common sense that you've got. Now, first of all, let's see where the NO actually comes from. Okay, now why is NO in urban areas? The reason that it's in urban areas specifically is because of the number of cars. Okay, so the one and probably the easiest way to do this is to actually encourage people to take public transport, because public transport transports lots of people with very little pollution. So public transport is a very good solution to the problem of cars in the urban areas, because that reduces the number of people inside there. So urban transport means less cars. Now, this is something for those of you that have done a little bit of extra reading in your rates, is actually to fit cars with special converters on the exhaust. These are called catalytic converters. Now, I want you guys to go do a little bit of reading, because catalytic converters are hugely important. Now, one of the reasons that platinum is so valuable is because every catalytic converter which is produced, and there's a big plant outside Rustenburg that makes lots of catalytic converters, because catalytic converters are legally required on all cars at the moment. And what they do is catalytic converters actually break up NO and they allow nitrogen and oxygen out into the atmosphere. They reduce the amount of carbon monoxide and the nitrogen monoxide released out into the atmosphere because of cars' engines. Catalytic converters are probably the biggest help. Now, before this happened, what you would find is that in cities without catalytic converters, you get these brown clouds which used to float over. And since the introduction, air quality has improved dramatically. So these two things can help reduce the amount of cars and hence the amount of NO. Now, let's get into some of that equilibrium arguments over here. Now it says, explain why the formation of NO is favored. Okay. Now this is starting to sound a little bit like the arguments I use in equilibrium. In internal combustion engines, where temperatures are as high as 2,400 Kelvin, so that's a very, very high temperature. So that's almost 2,000, well, it's over 2,000 degrees Celsius. Now, why would high temperature favor the formation of NO? But wait a minute, let's take a look at our reaction and let's see if we can't find some clues. Now, grade 12s, just a hint. When I see temperature, and temperature only, this is when I look at delta H. Guys, please don't be tempted to say, okay, delta H in pressure and delta H in concentration. Delta H is something which I only look at when I'm considering temperature and its effect on equilibrium. So here we go. Delta H, the heat of my reaction, is positive 90 kilojoules. What does that mean? This means that my forward reaction is endothermic. My forward reaction needs heat. So if I supply heat, the forward reaction will be encouraged or increased. Now, please don't say that an increase in temperature will favor my forward and the reverse will slow down. No. Both of them will increase in rate. However, the endothermic is always the most affected by temperature. Always. Now, my endothermic reaction needs heat, and it's going to be sped up. And that's the reason that my forward reaction will be favored. Okay, so here's how you answer this question. The forward reaction, first of all, is endothermic. An increase in temperature will drive or encourage a faster rate of reaction for the endothermic reaction. That means more product, and that's what they're looking for those 2 marks. Okay, so now we know that a high temperature favors the forward reaction. Okay, now here we're going to start getting into some numbers and some heavy marks over here. It says, during a research experiment carried out by initially adding, this sounds like a table, and we're going to get to it now, 1 mole of O2 and 1 mole of N2, so we're given 1 mole of each inside a 2 decimeter cubed closed container at 300 Kelvin. It was found that the concentration of the NO present in the container at equilibrium is 0.1 mole per decimeter cubed. Now we're asked to calculate the equilibrium constant, or Kc, for the reaction at this temperature. Now a lot of you are saying, okay, this is one of those tables, I'm just going to leave out the question. Guys, please don't leave these questions. I'm going to show you a few hints on how to construct your table, and even if you're completely lost, on how to salvage some of your marks. Okay, so here we go. Before we even get into the table, what I'm going to do is, the first important step is to have your balanced equation up at the top, and then we can start to make some judgments from there. So here we go. We've got N2 and we've got O2. There we go. They reversibly react to give me 2NO. Now remember that these are all gases, so that's quite important. I must know that they are all in that phase, because then they're all included inside my Kc calculation. Okay, guys, before we even do a table, you should be able to change this balanced chemical equation into a Kc expression. Sometimes it's called a mass action expression. So here we go. Let's just try and figure out how a Kc is done. A Kc is dependent on concentration of my products over the concentration of my reactants. Okay, so which one are my products and which ones are my reactants? Okay, well guys, my products are the ones which are found on the right-hand side. They are the ones which come out of my chemical reaction. So, I write the concentration of my products, but there's a trick. It's NO. Now what I need to do is I need to remember that my coefficient, the number on the front, becomes an exponent. So here we go. So that becomes an exponent on the outside there. That's what happens to that too. Now I see so many matrics, even the really studious, everyone calls them smart and whatnot, they forget that too and it ruins them. Guys, please remember that my coefficient over here becomes my exponent over there. So don't let that ruin you. And the very fact that you can do this will get you a mark in your exam. Now my concentrations of my reactants down at the bottom, and please matrix, don't be fooled into thinking that you add the reactants. Please don't. I know there's a plus inside your equation, but these are multiplied together. You multiply your reactants together, or you multiply your products together if there's more than one. There's no exponent on N2 and O2. Why? Because there's one N2 and one O2. So there's the equation which I'm hoping to fill. But now these square brackets need concentrations. And how do I get them? Well guys, now we've got to draw up a table. What I'm going to do is just come back to this a little bit later on, is I'm going to write out my reaction again, and I'm going to show you how to construct a table right from the beginning. So N2 plus O2, so I have a little bit of space over here, my reversible reaction, and my 2NO. Here we go. Now we're going to build ourselves a little table over here. So what I'm going to do is I'm going to give myself a little bit of space over here. So I'm going to start it off. Each one of my chemicals becomes the heading for a new column. So N2 plus O2. There we go. And then my products over there. Fantastic. We've got our three things and their headings for our columns. Now what we've got to do is we've got to have 4 rows underneath them. Okay. Now, you might ask me what happens inside these 4 rows. I'm going to show you exactly how to do this. I'm going to wait for you guys at home to do exactly the same as I do. So now what we've got over here is the basis for what I call a rice table. So here we go. R, I, C, and E. Okay, you might ask yourself, why a rice table? Okay, well the first one is to do with the ratio. Let me explain what I mean by ratio. The ratio is the ratio in which we combine our chemicals. So what I do is I take a look at my balanced chemical equation. I say 1N2 plus 1O2 goes to form 2NO. That tells me the ratio of my chemicals. So that's really important. Okay, now I, C, and E are to do with the number of moles. Initial, so at the beginning, how much they change, and then at the end, I call this equilibrium. So this is once they've reached equilibrium. Now we've got to go get some numbers and fill them in over here. Now remember that we're dealing with numbers of moles. So we've got to make sure that we're getting numbers of moles. Now let's go back to my description of my experiment. And then it says, during a research experiment, here we go, I got 1 mole of O2, so that's the initial amount of O2, and 1 mole of N2. So it's quite important that we know that there's 1 mole of N2 as well. That is the initial amount of both of those. Now it says they were put inside a closed container. That's quite important because this closed container didn't have any product. That's quite important. So let's put that in our table so long. So I know that initially I had 1 mole. I'm actually going to write in the moles here because I like to make sure that I'm understanding that there's moles inside this table. So 1 mole of each of those, and I didn't have any products over there. So there's 0 moles of products at the beginning. Okay, now the problem is I don't have any other information except later on in the question we're told that there's a certain concentration of NO. Now that's a concentration. That can't go straight into your table. That tells me that 0.1 moles per decimeter cubed of NO. Now what have I got to do? Well guys, I've got to change that into moles to be able to work on my table. 2 decimeters cubed of 0.1 mole per decimeter cubed, what I've got to do is multiply them to get the number of moles at equilibrium. So here we've got 0.1 mole per decimeter cubed times 2 decimeters, and that's equal to 0.2 moles at equilibrium. Okay, Now, this is what I'm looking for, guys. We've got our rice table set up. We've got all our pieces of information over here. Guys, this is exactly like a Sudoku puzzle. All you've got to do is look to see where you've got information and fill in the gaps. For those of you that haven't played the game, the whole idea is that you find the pattern, you find the missing number, and you fill it in. Now, the only place where I have enough information to actually fill things in is over here. So let's actually do everything new in purple. Okay. On our NO column, that's where I've got the most information. That's an almost complete column. I started with 0 moles. I ended up with 0.2 moles. The question is, how did I get there? Well, the solution is actually fairly simple. I must have added 0.2 moles by making it. So I manufactured or produced 0.2 moles. Okay. Now, let's take a look at how to fill in the rest of this table over here. Now, guys, I'm going to give you a bit of a hint, and this is something which confuses people. Change is due to my reaction, and it works on the basis of your ratios. Now, please don't fall into the trap that change, or at least initial or equilibrium over there, don't ratio any of the lines. The only line which you're allowed to ratio along is your change line. Let me show you what I mean. So what I've got to do is I've now got to take my 0.2 moles over here, and this is a confusing part. I've got to take 0.2 moles and use my ratio. Now remember, my ratios are written up here at the top. Okay, so now I'm going to ratio this. So the way that I do this is I say 0.2, I divide it by 2. So I divide it by 2, and then I multiply by 1, and it equals my final answer over here. So now that looks a little bit confusing, but basically this lands us up with 0.1 moles over here. Now, another thing to remember is that reactants are used. So that means that the change will be a negative one. Now let me just go through that ratio thing again, because it's probably the most confusing part of this table. Is that I need these two numbers in the change line to be exactly the same ratio as the one that I found for my chemical reaction. So 1 is to 2 as 0.1 is to 0.2. They should be in exactly the same ratio. Please, if you're struggling with ratios, practice them and practice them again. Even ask your math teacher to help you with the ratios. Okay, once again, we're going to ratio the very last one over there, negative 0.1 moles, because it's exactly the same ratio. Happy with that? Okay, now here comes the easy part. This is the very satisfying part. Is that to find the amount at equilibrium, all I've got to do is go through my columns. I take my initial amount of 1 mole, I subtract 0.1, and I land up with a final concentration, or at least an amount of 0.1 moles. And then an initial amount over here also leaves me with 0.9 moles. Okay, but now remember I said that you needed concentrations for your final Kc calculation, and we've got to change all of these into concentrations. So here's the formula that you use if you've forgotten. C is equal to N over V. So I'm going to divide all of these by 2, and we're going to find our concentrations. So 0.9 divided by 2 over there is equal to 0.45. Once again, 0.45. And then at this last one, we didn't even need to do it because we knew that initially that was 0.1. These are all concentrations which I can use inside my Kc. Okay, let's go back to my Kc calculation over here. So I say NO squared, and I was told that NO was 0.1. Don't forget to square it, please. Divided by concentration of N2, which is 0.45, concentration of O2, which is 0.45. Now let's put this all into our calculator. Let's find out what our Kc value actually is. So there we go. Let's put it into a fraction. Okay, so there we go. We've got 0.1 squared up at the top there, and down at the bottom there, 0.45 also multiplied by itself. Please don't add them, and we're going to get a value which comes out there. And this is a very low Kc value. So 0.45 or somewhere around about there. And we might be asked to comment on this. So 0.05 is a very, very low Kc value. Just remember that Kc is a ratio. There's no units inside it. Okay, so when you're dealing with these ratios over there, 0.05 is the way that we actually do this. I don't know if there's questions on the
While
page there
you're
about
there,
this.
Phil, yes, there's one that says, are the solids included in the Kc expression?
Really, really nice question. Okay, now when I come up with a Kc expression, remember I told you to see if they were all gases. When they're solids, their value is 1, their concentration is 1. So effectively, we actually leave them out of the Kc. Really, really nice question, Abram.
All right.
Okay,
Thank you.
so now that we've calculated our basic Kc over there, we're going to be asked a couple of questions over here. Now it says, how will the amount of NO at equilibrium be affected if? Now, the first thing that they ask me about is the pressure is increased by decreasing the volume. Okay, but now the way that pressure affects equilibrium is down to the number of moles. So remember I had 1 mole of N2 plus 1 mole of O2 going to make 2 moles of products. Now what you can see is that there's 2 moles of reactants, 2 moles of products. So what you will find is that the amount of NO won't actually change at equilibrium. And here's the reason why. There's the same number of gas moles on the left and on the right hand side of our equation. So what you will find is that for this one, there is no change. Pressure will not affect this equilibrium at all. And the reason for that is because an increase in pressure will speed up both the forward and the reverse reactions. Okay, now this one, I particularly like this one as well. A catalyst is added. Now you might say, okay, well, a catalyst is good, it makes my reaction really, really fast. But the question is, which reaction? A catalyst will speed up both forward and reverse reactions equally. So you'll reach equilibrium faster, however, the amount of product will remain exactly the same. So once again, there will also be no change over here. And that's a really nice question. I particularly like that. Please make sure that you understand the effect of pressure and catalyst. Now, sometimes pressure can affect your equilibrium, but catalyst cannot, because it speeds up both your forward and your reverse reaction equally, keeping the amounts of products and reactants exactly the same. Okay, and then one last one over here. So it says, we've got to draw the potential energy diagram for the above reaction. Now it says, indicate the heat of reaction and the activation energy for the catalyzed reaction. Okay, right, now this is something which comes from your grade 11 chemistry. What we're going to do is we're going to draw the energy profile. Okay, it's quite a quick thing. All you've got to do is you've got to come up with your chemical potential energy on the left-hand side. So this is your chemical potential. I think we're running short on time, so I'm going to be quite quick about it. So it's chemical potential energy. And on the bottom here, you can either talk about time or something called a reaction coordinate. So it's where you are in your reaction. So a reaction coordinate is telling you either you're at products or reactants. Okay, so let's be quite quick about this. All that we've got to do is we've got to realize that we start out with a certain amount of energy in N2 and O2, but that we ended up slightly higher than we did. So what happened is that we stepped upwards. Remember, it was an endothermic reaction. So the things that they want us to mark out over here are the difference between initial and final, and that change is called my delta H. And then they wanted us to plot out a catalyzed reaction. And remember what that does is that drops your activation energy and leaves you in the same place. So my activation energy is going to drop. And that is my catalyst, which made that difference. Guys, unfortunately, I've enjoyed myself, but we are running out of time. I hope that you've enjoyed your exam sessions over here. Abram, it's been great.
Thank you very much, Phil. And you know what, on the page, mindsetters have been just checking up what you're saying. You make things simple, and I like that. But also, what are your words? Because some of the mindsetters are writing their test on Monday, in encouraging them.
Well, guys, matrix, please just relax yourselves. Practice a few past papers, but please don't stress yourself out. It's actually going to make you do worse. Just chill out, go through your past papers. Practice, guys, it's the key.
That's the key. Practice and make sure that you go over mindset past lessons that we're having on YouTube, and also visit our Facebook page, which is facebook.com/learnextra. Also remember, on that page, you can let us know what are your wishes for your dad on June 16 as we're celebrating Father's Day and also Youth Day. So all the details are on the Facebook page. If you missed out on the notes, go to learnextra.co.za/live. We thank you so much for taking your time and tuning in. Have a great Saturday.